Thank you very much for this kind invitation. Actually, I wish I could visit you in person, but this will have to suffice. So in this talk, I'm going to discuss about the genetic algorithms and their cosmological applications. So first, I will give a very brief introduction to the standard cosmological constant, to the standard cosmological model, and then also then to the genetic algorithms. Then I will present some applications of the genetic algorithms to the background expansion of the universe and the large-scale structure of the universe. And if there is some time, then I will present some results from forecasts of Euclid, some null tests, and also some very nice fitting functions. Okay, so before I actually start, I would like to say a few things. First of all, the bulk of the recent work was done in collaboration with my PhD student Ruben, who graduated in September 2021, so last month. And there has been lots of work with some past and present collaborators, including Juan Garcia Bellido, the Euclid theory group, WP5 and WP10, and many other people. And there has been a plethora of genetic algorithm papers since 2009 and until actually this month. Okay. So first, as I said, I will give a very brief introduction to the standard cosmological model. So as we all know, the standard cosmological model is based on two pillars. First of all, the Einstein equations, which are expressed in terms of the energy momentum tensor on the left-hand side. They also have the cosmological constant and the energy momentum tensor on the right-hand side. And also, it's based on the assumption that the universe is homogeneous and isotropic on very large scales, which implies that we can use the Friedmann-Lemaitre-Robinson-Wautier metric, which depends on the scale factor, which is a function of time, and tells us how the universe is expanding on large scales. And of course, it depends on the curvature. Now, the curvature can be 0 for a flat universe or plus and minus 1 for a closed and open universe. And if we use the Robinson-Wautier metric and the Einstein equations, then we can get the Friedmann equations, which relate the evolution of the universe through the first derivative of the scale factor on the left-hand side and the energy content of the universe on the right-hand side. And of course, we also need the continuity equations, which tell us how the energy density of the various particles evolves with time. Okay. Now, there were two key observations. First of all, by Hubble in 1929, who realized that the universe is expanding by the redshift of distant galaxies. And also in 1998, by Riss et al., who realized that the universe is also accelerating by using type 1a supernovae, which means that if we use the second Friedmann equation, this implies that if the universe is accelerating, this has to be positive. And since we have a minus sign there, then the sum of these two things, the pressure and the density of the species in the universe, has to be negative, which means that the pressure has to be smaller than minus rho over 3. And if we introduce the equation of state, which is 0 for non-relativistic matter and 1/3 for relativistic matter, then this means that the known forms of matter cannot explain the accelerated expansion of the universe, because non-relativistic matter has W equals 0 and relativistic matter has W equals 1/3, and this has to be minus 1/3. Okay, so we need something which has an equation of state smaller than minus 1/3. Okay, in order to explain the accelerated expansion. And finally, if we go back to the first Friedmann equation, which is written in this form, and we introduce the so-called fractional density parameters, then we can write it into this nice form, which only depends on the scale factor and the density parameters, the omegas, okay, which are dimensionless. Now, what are, let's say, the values that we have for these parameters from observations? So we know that recent observation suggests that practically all the visible matter that we see, like the planets and the stars and the gases, is roughly 4 to 5% of the total energy budget of the universe, which means that omega baryon is around 5%. Then from observations, we know again that the dark matter is around 25% of the energy budget of the universe, which means the omega C here is around 25%. Omega radiation is on the order of 10⁻⁵. We assume also that the universe is more or less flat, so this has to be 0. And then for the omega dark energy, this is on the order of about 70%. Now, the fact that practically 95% of the energy budget of the universe corresponds to unknown forms of matter and energy, this has led to the very nice creation of dozens of theories in the last 30-something years. Actually, in terms of just only for the dark energy, we have like all these kinds of models that try to explain. So we have theories beyond general relativity, like covariant modifications of GR that have higher order corrections. We have theories where graviton is massive, or theories where gravity is non-local, or we have extra metrics, or the vacuum is running and so on. Of course, we can also have coupled, minimally and non-minimally coupled scalar fields to gravity, or theories with extra dimensions. And this only takes into account the models that try to explain dark energy. So we also in practice have as many more or even more models that try to explain dark matter. Okay, so we have a plethora of models that try to explain the dark components of the energy budget of the universe. And this actually, even though for theorists is very nice and stimulating, in practice, this causes a few problems, in my opinion. So the two kinds of problems is that, first of all, we can only test a limited number of models, because practically there's an infinite number of theories. I mean, I can always cook up realistic or semi-realistic theories. And in practice, you can never test all of them. You can only test a limited number of them, because, okay, if you want to compare with observations, you need to have Boltzmann codes. And of course, it takes some work to create likelihoods and all this stuff. So practically, this limits us to only a certain number of models. So practically, we might have, let's say, a theory, a very realistic theory that explains dark energy, even the ultimate theory of gravity that can explain dark energy, which lives somewhere on the periphery, like on the very far away, and we will never see it, because practically we can never test everything. We can only test a few things which are near or around the GR. So for example, if we need n-body simulations, we only have n-body simulations for GR, and now I think there are also some F of R n-body simulations. And also for Boltzmann codes, there are Boltzmann codes for GR and some dark energy models, and also for some Hordensky models and so on. But we don't have Boltzmann codes, for example, I don't know, for the DGP or whatever. Or perhaps there might be some obscure code, but it hasn't been updated. But we only have codes for the mainstream models, let's say. So practically, it's very difficult to test everything. Okay. And another issue, which is quite important in my opinion, is that we can have model bias. So the interpretation of the results can depend on the model that we assume. Okay. So for example, if we use the lambda CDM model and we find that omega matter is 0.315, this is actually model dependent statement. Okay. Of course, if we assume that lambda CDM is a good description of nature, then we can make the leap of faith and say, okay, maybe the matter density in the universe is very close to this number, but this might not necessarily be the case. Okay. So is there any solution to these two kinds of problems? So we can actually attack the problem from two approaches. First of all, a top-down approach, but also a bottom-up approach. So a top-down approach would be to use an effective field theory or an effective fluid approach and try to test modified gravity and dark energy models, like in whole classes of them, okay? Because that's a bit easier. And people have created lots of codes, even Boltzmann codes that work within the IFT framework. Okay, I think Sandra Silvestri has some codes for that. Another approach, which is more data-driven, is to consider a bottom-up approach. So we could use a machine learning approach to see what the data tell us about these theories that could explain dark energy, for example. And in this talk, I'm going to focus mainly on dark energy. And this could be useful because, as I said, we have so many models, but the real model could be somewhere up there on the left or the right or outside our mainstream models. And they might have some features that we might miss them because we don't have time to test everything. Okay, but the machine learning approach might be able to discover some of these features, and that could be very useful. Now, these two approaches are, of course, they're obviously complementary, okay? And I'm not really suggesting that we could use machine learning to replace theory. Of course, I'm also a theorist myself, partly. So, but this could be complementary approaches where we could use either an EFT framework to test whole classes of models, or we could use a machine learning approach to try to find some features in the data which perhaps we have missed, okay? Because now the data are becoming more and more complicated. And we are in the era of big data, and it's very easy to miss some subtle feature, okay? So I think using both approaches at the same time to attack the problem is really necessary, okay? Now in this talk, I'm going to talk about machine learning, so I'm not going to focus on the theoretical aspects. And the question is, what is exactly machine learning? So machine learning has become quite popular in the last maybe 5-10 years, and people have been throwing around buzzwords all the time, but what is exactly machine learning? Okay. Now, one of the best definitions of machine learning that I have found is actually one that exists in Wikipedia. And Wikipedia defines machine learning as the study of computer algorithms that improve automatically through experience. And this is a subset of artificial intelligence. And I really like this definition because it is very clear, it's concise, and it's to the point. Okay. However, machine learning still includes, it encompasses a large plethora of different approaches one can use. And largely they can be categorized into three categories. So one is reinforcement learning, the other is supervised learning and unsupervised learning, and each of them branches out and it has very different subcategories. Okay, and of course these categories are not very sharply defined, let's say, so they sort of talk with each other. So there can be some semi-reinforced approach of supervised learning or semi-supervised learning with reinforcement learning and so on. So these things communicate with each other, so they're not very, the bounds are not very sharp, if I can say it like this. However, not all of them are very useful for physics, at least for the things that we want to do. So for example, reinforcement learning is mainly used to train robots and maybe train video game artificial intelligence, so how to learn from the player in order to beat them in the video game and so on. So for physics, they're not very useful. So what is very useful for physics and cosmology and astronomy is supervised learning and unsupervised learning. In particular, supervised learning because you can use it to classify images and so on. So for example, you can train a neural network to learn to identify spectra or galaxies or gravitational wave templates or so, and so on. So for example, you can train the neural network to classify the galaxies into, I don't know, spiral galaxies, elliptical galaxies, and so on. And this is very important because future surveys like Euclid and so on, they will take images of hundreds of millions of galaxies, and obviously you cannot really classify them one at a time and so on, and manually, more importantly. And the other approach is unsupervised learning, where you can use the machine learning to try to discover features in the data and try to discover structures that may not be so obvious. And this is very useful, in particular, as I said, for dark energy, because we don't really know what are the properties of a dark energy. Okay, we know that it has to cause the accelerated expansion of the universe, but it could also have some other properties which are not so obvious a priori. So we could use the machine learning and the unsupervised learning in order to try to discover some of these features, okay, as a complementary approach to the theory, of course. And one particular approach which is very useful for this, and it's something that I have been working on since 2009 practically, is the so-called genetic algorithms. Okay, so the genetic algorithms are a category of machine learning which are inspired from evolution, and I will explain in a moment how they work. What are the advantages, the disadvantages, also some similarities they have with Monte Carlos. And actually, I will also show you a simulation more or less in real time, how they work and what you can learn from them. And then I will also show some results. Okay, so what are the genetic algorithms? Now, from now on, I will refer to the genetic algorithms as the GA. I don't want to say genetic algorithms all the time, so I will refer to them as the GA. So the GA is a stochastic optimization approach, and as I said, it's very similar to a Monte Carlo. So stochastic optimization means that stochastic is random, and optimization means that we are trying to minimize some function. Now, for us, this is usually a regular chi-square, okay? But in principle, in other fields, it can be whatever. Okay, so the idea you have to remember is that it's just a stochastic optimization, which is quite similar to a Monte Carlo. Now, why are they similar to a Monte Carlo? They are because in the Monte Carlo, as you can imagine, I guess everybody knows how Monte Carlo works. So you have a model with some parameters, and what you do is you do a random walk, okay, in this parameter space. Now, the idea behind the genetic algorithms is that you do something similar, but now you don't have a model. What you do is you have a set of functions, and you are exploring the functional space. So it's a bit more abstract, okay? And I will explain in a moment more what I mean by this. And this fact that we write with the genetic algorithms, we don't really have a model, but we are actually trying to find the model itself because we are exploring the functional space. This has the advantage that the GA is not biased by some a priori selected model like lambda CDM or some other specific model. And also it's not biased by any assumption. So as I will mention in a moment, we don't have to assume flatness, we don't have to assume anything. Okay, so practically we can fit, for example, type 1a supernova data. We'll show an example later, and we don't have to assume that the universe is flat. I will just take the data, fit them, and get a function. I will show you in a moment. And they have very strong mathematical foundations with several rigorous theorems, some of which I will very briefly discuss later. And you can see more details in Wikipedia. Actually, Wikipedia has some very nice articles on this. And also they are very accurate and very simple to implement, but of course require a bit of CPU power. So the required CPU power is on the order of a traditional Metropolis Hastings Monte Carlo. Okay, so let's go one step at a time. So as I said, the GA are very similar to MCMCs, and both of them do stochastic or random optimization. So as I mentioned before, just to visualize things a bit, in the Monte Carlo, you have some model with some parameters. Let's say it's X1 and X2. And then what you do is you do random walks in this parameter space. And as the particles, they move around in the random walk, you are sampling from the posterior, and practically you can get the confidence levels, you can get the confidence contours, you can get the best fit and so on. Of course, Monte Carlos are not very good for the best fit, but I mean, you can get some, maybe the mean values that would be more accurate. And then you can get the covariances and the errors and so on and so forth. However, in the genetic algorithm, there are no parameters like that, but instead you have to imagine, you have to visualize in your head that, okay, we have functions. Okay, of course, this is a bit difficult to visualize. We cannot really visualize abstract, infinite dimensional functional spaces, but let's assume that here you have a set of functions like sines, cosines, and here you have some polynomials, and you are moving around in this space. And then you can also get, in this case, the best fit, and you can get errors and so on and so forth. So if we want to make, let's say, a dictionary between Monte Carlos and the genetic algorithms to translate from one to the other. So in the Monte Carlos, you have parameters. In the GA, you have functions. In the MCMCs, you have best fits, which correspond to a point. Here you have best fit functions, which corresponds to a line. So for example, here I'm showing the distant modules of supernova as it has been reconstructed by the genetic algorithm. I will show some more details later. And the best fit is the solid black line, and you can see fits quite well with the data with respect to lambda CDM. And of course, in the MCMC, you get confidence contours. Here you get error region. So this is the gray shaded region. Okay, this is your error, 1 sigma errors. Okay. Now, how do they work exactly? So the way they work is, as I said, now instead of parameters and models, we have functions. So what you do is, if we have some data, then what we do is we set up our grammar. So the grammar is the set of functions that we want to consider. So for example, we could consider like polynomials, fractions, sines, cosines, exponentials, logarithms, and so on. Okay. And what we do is at the very first step, we take all of these functions and we throw them at the data and we calculate their fitness. So their fitness is just the chi-square. Of course, as you can imagine, in the very first generation, in the very first attempt, if you just take any random set of functions, the fit is going to be crap, horrible. I will show you some example later on. It's actually in the millions or billions. Okay, so it's going to be really bad. And the idea behind the genetic algorithm is that we try to imitate nature. So we take these functions that we have originally in the very first step, and what we do is we select the best of them, like similarly like what happens in nature in evolution. Only the fittest survives, and then we reproduce them with a process called the crossover and the mutation. Okay, the mutation is actually a small change, like again happens in biology. So you change, for example, X might become X squared and so on. And then we iterate this process and we go to the next generation hundreds or thousands of times. And we see that our set of functions, initially they may have been like simple polynomials, but as we iterate again and again and again, and I will show you a simulation in a moment how this happens, we see that the chi-square, their fit, becomes better and better and better, and they actually start fitting the data very nicely. And then we can get a very smooth and analytic function that fits the data very well. I will show you an example in a moment. First, I would like to explain a bit what is this selection, how this selection happens, and what is exactly the crossover and the mutation. I will show you exactly what are these. So about the selection method, so if we have a group of functions, how do we select which functions will survive and then we'll move on to the next, let's say, round or to the next generation? So in the literature, there are two approaches. One is called the roulette wheel selection, where the selection probability is proportional to the fitness, but even though this is widely used, this has the problem that the suboptimal solution may dominate the mating pool. So for example, you might have a function which is good, but it's not good enough. And then your genetic algorithm might be stuck, let's say, in a fake minimum. You might be stuck there and you never move, okay? So personally, I don't like this very much. On the other hand, you have the so-called tournament selection, where from all the functions, you just keep, I don't know, the 10, 20, 30%, the best of them, okay? So you have some variety, and this is very easy to implement. It is in line with natural selection because only the fittest survive. And of course, in this case, you can avoid the premature convergence. Okay, this is at least my codes. This is what I have implemented. It worked quite well. Okay. Now, what is the crossover and the mutation? Now, assume that we have taken our best sample of our best fit functions. We want to actually to mate them. Okay, and what happens in evolution, in what happens in nature, is that if you have the parents and they have the chromosomes, then what you do is you have some part of the DNA of your mother and some part of the DNA of your father, and these things are mixed. Okay, this is how it works in biology, and we do something similar in the genetic algorithm. Okay, so imagine if we have some function like the logarithm of z, and we have a polynomial of z, and then what we do in the crossover is just split them up at some point and we mix them. So you might get like logarithm of z squared or -1 plus log z squared and so on and so forth. You do combinations like that. So you take like 30% of your best fit functions and you just split them up at some point and you mix them up a bit. So just to introduce some variety, let's say, okay? And this happens randomly. You don't do it by hand. Okay, so you pick random numbers and you do all this stuff. So everything is fully automated. And finally, to introduce even some more variety, what you do is you apply the mutation operation. So if you have a function which is -1 plus log z, so you might randomly change the z to the cube, or the plus to, you might change it to a minus, and so on and so forth. And again, this is similar to what happens in nature. So you might have some bacterium that lives happily, but it's hit by some X-rays or whatever, and then it mutates, and I don't know, it can have different properties, and so on and so forth. Again, everything is practically motivated by what happens in evolution, but at some point I would also like to stress that we are not really constrained by evolution. This is just a mathematical process. I mean, it exists separately from evolution. So in principle, we could have discovered the genetic, we could have invented, not discovered, we could have invented the genetic algorithms independently from evolution. Okay, so we don't really depend on evolution. Okay, this is just inspiration. So, okay, let's see an example now. So let's make some mock data, and here I'm going to show you very quickly simulation. So let's make some mock data. By the way, I forgot to mention that if you have any questions, please ask me, don't hesitate. Now let's assume that we have some mock data. In this case, I cooked up a model which is like a plus x minus b exponential minus cx squared. And I chose this because it has some nice features. So it goes up, then it has a maximum, then it goes down again, okay? It has some nice non-trivial features. And I chose the parameters 0.25, 0.25, and 0.5. And then we can make some mock data based on this. Now, if we take this model, the real model, let's say the underlying the real model, and we fit it back to the mock data, then we can find, for example, that the best fit parameters A, B, and C are this, and the chi-square per degree of freedom is very close to 1, which tells us that obviously the real model is a good description of the mock data. Okay, this is something we expect. Now let's see what happens with the genetic algorithm. Okay, now I'm going to switch away from the slides. For some reason, I cannot minimize this. Sorry. Okay, let me switch to Mathematica. So I have a code in Mathematica that does the animation. So
yeah, we can see it. Okay,
perfect. So I have already run the genetic algorithm. We don't want to wait for like, I don't know, half an hour for the code to run. So I have already run it, and I'm going to play back an animation. Okay. So in these two plots, you will see the two following things. So these are the mock data. The red and the green lines are the real model and the best fit model when we fit the real model back. Okay. The solid black line is the best fit of the genetic algorithm in any generation. So I'm going to run the animation, and we will see what happens after every generation, like generation 1, 2, 3, blah, 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 all the way up to 100. And you will, just to know what to expect, you will notice that the black line goes closer and closer to the points. Okay. Now, in this case, I'm going only to show you the best fit function in every generation. And later on, I will also show you all the functions to see what happens. So I will just show you the best fit function in every generation. So just from all the possible functions that you can come up. Actually, perhaps I can just show you the functions. So in the very first step, as I said, you take your grammar, like polynomials, fractions, and whatever else you want to include, and you just cook up random functions and you throw them at the data. Okay. Now, out of all of these functions in the first generation, the best one happens to be, for whatever reason, this one. It's 2x minus x squared. Okay. And you will notice that as the generations go by, then this function will change, and also the chi-square will keep falling. Okay, it should go in the order of 30 something. And here I'm showing the chi-square as a function of the number of generations, and you will notice that it will start going down and down and down. So the red point there will move and will start falling along this blue line. Okay, just to know what to expect. So let me run the animation. So this is the first generation, and it will keep moving now. It's going to fall. Okay, you see the next best function is x over x plus 1. It's falling again. It's a bit more complicated. It fits slightly better, and now it's x to the x plus this. Now there is a region which is a bit flat, so there is a plateau. Okay, so the population is more stable. Okay, there are some things happening, but the best fit doesn't change very much, and then it's falling again. And then it's a bit more complicated. So you see the chi-square is now also like on the order of 70. Okay, perhaps I can speed it up a bit. We don't want to wait forever. And then it's falling again. There are small plateaus, and it's falling again. You can see it's becoming more and more complicated, and then it fell again. And then it remains here. And then because this is quite flat, it remains there practically forever. Okay, I can stop it. And then you can see now the black line falls almost exactly on top of the real model. Now you will notice that I mentioned in the slide that the real model was actually a plus x minus b exponential and so on. And the model that the genetic algorithm found was like x over x to the x plus x, blah, blah, blah. So the genetic algorithm didn't really, let's say, discover the real model, but it will give you a very good description of the data, which is analytic and smooth and whatever. You can do whatever you want with that. Okay. So it never, okay, in some cases it can, in some constrained cases, it can discover the real model, but in general, it cannot. I mean, the actual function, okay? But it will give you a very good description, which is very close to that one. Now, let's see what happens to all of the functions in every generation. So you can see there are many functions like 1 plus x. So you can imagine like 1 plus x is just a straight line that goes up. So it's obviously not a very good description of the data because the data have a maximum and then they start going down a bit. And there are also some other ones which are a bit more crazy, like fractions, and one which is just one, just a number. So let's see what happens. So I will play the animation. You will see these things that will change, and they change because we have to apply these operators, the crossover and the mutation. So some of them, they will start doing crazy stuff. So let's see what happens. Okay, some of them now are just x, but they're also just square roots, and they change. Now we have like x to the x. This x to the x appeared. And they become a bit more complex. And then, oops, it stops there. And now we have the function which is our best fit, x over x to the x. Let's see if we can try to find it. So it's maybe this one. No, it's 2x. Yeah, it's somewhere in here. I'm not sure I can find it right now. It's somewhere in here. But you can see we also have other functions. Some of them are quite bad. The ones somehow still survived. Okay, surprisingly, even 0 is in there. Actually, the way you can understand this is that, I mean, evolution is not, let's say, a perfect process. It's a stochastic process. And in real life, you even have some samples, some individuals in a population which are not so fit in them, but somehow they manage to survive because, I don't know, they are lucky or they have found some small niche and they manage to survive in this niche and so on and so forth. Okay. So this is how you can imagine it. And of course, there are some other functions that fit the data quite well. I mean, I should really try to find it. It's x to the x plus x over that. It's somewhere one of these, I think.
Can I ask a quick question?
Yeah, of course.
Why aren't there any exponentials in your table?
Well,
that was part of the underlying model. That's a simple function.
Yeah. So in this case, I didn't include them in the grammar. In the grammar, I only included polynomials and stuff like this, like x to the x, and what else? And fractions and stuff like that. I didn't include the exponentials. In principle, you can also include exponentials for sure.
Okay, so the point of this example, I guess, is it shows a good fit can be found even if your grammar is slightly wrong.
Yeah, even if you're exactly so. Even if your grammar is very simple and it's in the real model is not in your grammar, you can still get a fit which is amazingly good.
Okay.
Basically.
Right.
Yeah. Thanks. And one last thing about the simulation, because I also want to talk about other stuff. Here I'm showing the chi-squares. Okay. Now you can see the chi-squares of every function in the population. Some of them are reasonably good for a first guess, I mean. So you can see like they're like a few thousand, which is not so bad for a random guess. Some of them are on the order of billions. This one is like, it has a chi-square of 2 billions. Okay. Yeah, it's quite crazy. And you will notice as the animation plays, this will start going down, and you should notice that the average chi-square, not the individual, but the average, will keep reducing and reducing and reducing. I mean, you will see what I mean. Okay, let me play the animation. Okay, it already dropped to a few thousands. Okay, now it should start going below a few thousand. Now it's 500 something. At some point, it was even complex for a moment. It's doing indeterminate. It's doing crazy stuff. Exactly. Okay, I can speed it up. Again, we don't want to wait forever. Now it's on the order of a few hundreds. Okay, again, there was a complex there for a moment. Determinate, complex. Now it's around 50. Let's see, we have 30 there, which is actually slightly better than the real model. And many more of them are now around 30. So you see, the real model, which is like 30 something, has a chi-square of 30 something. It appears in many places, but again, you still have some functions which have a really bad fit, like 20,000. There's one which has like 6 million. Some of the very bad fits still survived. Now, the reason why yeah.
Sorry. Can I ask if there's using some rule for each iteration, offspring versus mutation, or are you allowing that to be random as well?
Yeah. So usually for stability reasons, you have to limit the number of functions that get mutation. For example, if I remember, to like 10% or something like that. So if more than 10% of the functions mutate, then the algorithm becomes unstable, which is also realistic because in life, you don't have like 100% of the population getting mutations all the time. All right. I mean,
but all of these are offspring of the best chosen ones from the last age step. Okay.
Yeah, exactly. Yeah. And what I was saying, and the thing is that sometimes you get some random weird crap. Where was like billions somehow appeared? There was like a complex thing. I don't know if I can find it now. Okay, there was one which has a complex chi-square, which is really difficult to get a complex chi-square because sometimes you might get something which is like I don't know, x to the square root of minus x. It might appear. I mean, you never know, right? And then this will start popping up like complex values and so on and so forth. And then, but this, as you saw, this dies off quite quickly. I mean, so you don't have a problem with that stuff. And of course, if you want, you can enforce some sort of, let's say, physical prior. So for example, you might say for physical reasons, okay, perhaps the value of this function at 0 has to be 0. For example, if this was a luminosity distance, the distance at redshift 0 really has to be 0. There's no other way. I mean, otherwise it doesn't make any sense, right? So you can impose some stuff like this, physical priors, in order to limit the amount of craziness that you get in your simulation. Okay, so this is enough with the simulation. I hope this gave you an idea how the GA works. Okay, now let's move on a bit. And okay, just to summarize what we saw in the simulation. So the real model was some exponential, which had, it was going up, then it had a peak, and then it was going down again. Okay, so it had some non-trivial features. The The real model, when we fit it back to the data, to the mock data, it had a chi-square of order 31.8 or a chi-square per degree of freedom of order 1. So obviously it was a really good fit to the data, and the best fit from the genetic algorithm, it looks like this, which has a chi-square which is on the order of 30.76, again a chi-square of degree of freedom close to 1, okay? And this is quite a good number. So we can see that the genetic algorithm performs equally well as the real model, and you might have noticed that I made no assumptions about the underlying, let's say, physics of the model. So I didn't assume that it has to go up, it needs to have a maximum or whatever. So, for example, we don't, in real data, we don't have to assume that we have some specific dark energy model, we have flatness or whatever. We don't have to make assumptions like this. So we just take the data, throw it at the genetic algorithm with some very minimal assumptions like that. I said that, okay, at 0, perhaps it has to be 0. Otherwise you get nonsense. But other than that, we don't really have to make any strong physical assumptions about the model. And in the end, we get a function which is a very good description of the data, and we can use it to do whatever we want, like take derivatives, blah, 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 all this stuff. Okay. Now, the question is, okay, we got some best fit function, but what happens about the errors? How do we get an error estimate about this function? And the way to do this is the following. So back in 2012 with Juan Garcia Bellido, we developed a path integral approach. So you have to remember that, as I said, the genetic algorithms are similar to traditional Monte Carlos, and we can use this Bayesian approach in this case. So for example, in Monte Carlos, in the Bayesian sense, I mean, we can just define a likelihood, which is e to the minus chi-square, and this would depend on some parameters. Here we can still define a likelihood, which would be direct function of the various functions that we're going to test. Again, we have a chi-square and the likelihood and whatever. Now, if you want to actually, for example, normalize the likelihood and get error estimates or whatever, practically you need to integrate overall the parameters, okay? So this is what you need to do this is what you do in a Monte Carlo practically. In the genetic algorithm, we need to integrate over all the possible functions. And integrating over functions is practically a functional integration, which in the physics language, this is actually a path integral, what we call in field theory path integral. And in this case, you cannot just integrate your likelihood analytically over all the functions. You can just do this path integral. We have the details in the paper. I don't want to, actually I'm running also a bit out of time, so I don't want to bore you with the details. Okay, I'm going to skip this. I'm just going to say there is a nice analytic expression you can use, and you can also generalize this to data with correlation and covariance matrices and so on and so forth. So everything is quite nice and analytic. Okay, and then we have also tested that this approach, this so-called path integral approach, works quite well. So we compared it with Fisher matrix methods and bootstrap Monte Carlos, and the results we get from the genetic algorithm are comparable. Okay, we don't get like crazy big or crazy small errors. So this approach has been well tested. You can see some results in the paper. I don't want to waste any more time, and we can discuss later if you have some doubt. Now let's discuss some applications to the real cosmological data. So can we use the genetic algorithms with real data? And the answer is, of course, yes. So we can use most kinds of data. So for example, type 1a supernovae, cosmic chronometers, baryon acoustic oscillations, growth rate, or EG data and whatever. Using the CMB is a bit tricky, at least the full CMB, like the Planck likelihood, that's a bit tricky. I haven't found a way to do that, but I'm planning to do that in the coming months, or if I manage to do it somehow. But of course, in that case, one could use, for example, the compressed CMB shift parameters. If someone has some questions about this, we can discuss later. And then the question is, what do they tell us about the universe? So for example, stuff like type 1a supernovae and cosmic chronometers and so on, they tell us about the background geometry of the universe. Stuff like about the growth rate or the EG data tell us about the evolution of matter perturbations and the large scale structure. And how can we interpret these reconstructions? And I will show an example in a moment. This actually depends on the data. So for example, from the cosmic chronometers or any other kind of H of Z data, we can get, for example, the Hubble constant, or we could get the deceleration parameters and so on. From supernova and BAO, we could get the luminosity distance and angular diameter distance. Again, I will show an example in a moment. From the growth rate data of sigma 8, we can get the dark energy and isotropic stress and so on and so forth. I will show some very brief examples in a moment. Okay. and some very mild assumptions that we can do. As I said, unless we want to get nonsense, we have to assume, for example, that the Hubble parameter at redshift 0 is the Hubble constant. It has to be a constant, obviously, okay? And of course, for the luminosity distance, we have to assume that the luminosity distance at redshift 0 is 0. And because the Hubble law is a fact, we can also assume that the luminosity distance at small redshifts is proportional to redshift, okay? So practically that the derivative is practically 1 or proportional to C over H naught, okay? And similarly for the angular diameter distance. Now, one other, this is a bit trickier assumption, is that we can assume that the universe at early times went through a phase of matter domination at the redshift around 100, which means that the growth at high redshifts goes like A, okay? I agree this is a non-trivial assumption, especially if we are working with early dark energy, but it's sort of reasonable. And of course, we can debate it. I mean, how reasonable is this? Okay. And what we can do is, as I said, we have all of these kinds of data like type 1a supernovae, BAO, Hubble expansion, cosmic chronometer data, growth, e.g. statistics. And in a paper with my student Ruben, we mapped out all the possible kinds of information we can squeeze out of the data. So for example, from the baryon acoustic oscillations, from the BAO data, for example, we can get a model independent estimate of the sun horizon of the drag redshift. From the cosmic chronometer data, we can get the transition redshift from the acceleration to acceleration. From the growth rate data, we can get the growth index. I will discuss some of these in a moment. We can get the equation of state, the acceleration parameter, and so on. We can get lots of stuff. So in the paper, we mapped out all the possible stuff that we can get. Now, in the remaining 5-10 minutes, I'm going to discuss some specific examples. So for example, there are some particular compilations of Hubble parameter data, the so-called cosmic chronometers. And these compilations, you can find this compilation in this paper with my student Ruben. We have the Hubble parameter at various redshifts from practically 0.07 all the way to 2.37. And these data, they come either from the so-called redshift drift, okay, from passively evolving galaxies, the so-called cosmic chronometers, or they come from BAO and the Lyman alpha and so on. So we have more details in the paper, and you can go also to the respective references that we have here. And you can see, for example, from the points from Moresco et al., you can see exactly how they derive the data and so on. Okay. And what you can do with this is that if you plot them, so first of all, they look like this, and obviously lambda CDM is a very good fit. So lambda CDM is the dashed line, and you can see it fits quite well. And if you throw them at the genetic algorithm, you can get a function that fits this data very well. Okay, so this is the solid black line. Okay. And another example that I'm going to mention also in a moment is the type 1a supernovae. Now, the supernovae are standardizable candles that result from explosions of white dwarfs when these reach the Cedras-Hart mass. And from these, we can get actually the luminosity distance. However, there is a degeneracy with respect to the absolute scaling, and we can only get information on the dimensionless luminosity distance. So the scaling, we need some anchoring from the CFITs or whatever to get it. But still, this is good enough to constrain dark energy models, okay? And what we can get from the genetic algorithm is a function that describes the dimensionless luminosity distance, okay? Which practically in these kinds of models is related to the integral of 1 over the Hubble parameter, okay? And in this case, again, you can take, for example, the Pantheon compilation. We have some more details in the papers. You throw them at the genetic algorithm, and then this gives you a function of the luminosity distance, which fits the data quite well. So practically, how do the best fits look like? So in the case of the cosmic chronometers, as I said, we can get the Hubble parameter. In this case, it looks like this. So it's a function of redshift with some numbers, okay? And in the case of the luminosity distance, it's a bit more complicated. It also has an exponential and so on. Now, someone might say, hey, I can see parameters there. So this is not a model-independent non-parametric approach. I can see numbers. But the thing is, as I mentioned, we didn't put these numbers or these parameters by hand. This came from the genetic algorithm. I showed you in the example, I didn't put any numbers or free parameters to minimize. These numbers, they came from the genetic algorithm, okay? So there are no free parameters, there are no model or very few or mild assumptions and so on. Okay. And as you can see here, I'm showing the chi-square with of the genetic algorithm best fit functions with respect to the one from the lambda CDM model. And you can see, for example, from the supernova, we get the chi-square of with the Pantheon data of 134, and the genetic algorithm gives a slightly better chi-square, and the same for the cosmic chronometer data. And the question is, now that we have some fits, what do we do with these functions? Okay, I have a function of a redshift. What the hell do I do with that? Sorry. So what do we do with that if I have a function? So for example, if I give you a smooth and analytic function of the Hubble parameter, I can just take derivatives, and I could calculate, for example, the deceleration parameter. Okay. And if you do this exercise, then you can plot the deceleration parameter as a function of redshift. It's just one derivative, okay, first derivative. And then you can get, for example, a 4.5 sigma model independent evidence for the accelerated expansion of the universe. I mean, it's quite clear. And you can also measure the transition redshift from the acceleration to acceleration. And we found that it was 0.662 plus minus something. And for this, we didn't have to make any assumptions for a dark energy model or flatness or anything. Okay. And now also you can do some more things with the Hubble parameter. So for example, if you have the Hubble parameter, you could also test the so-called Ohm statistic of Shaffelou et al. What is the Ohm statistic? So the Ohm statistic is a test of the lambda CDM model. So if you write down the Hubble parameter for the lambda CDM model, and you ignore neutrinos and stuff like that, then you can write it in terms of omega matter. And if you solve for omega matter, then you can get an expression for the Hubble parameter and just redshift. And this has the advantage that this has to be constant at all redshifts. So equal to omega matter. If this is not constant and equal to omega matter at any redshift, then it means the lambda CDM is falsified practically. And we have tested this in the paper with Ruben, with both real data and also forecast data with DESI. Okay, and you can get very nice constraints. Now I'm running a bit out of time, so what I want to say in the end is we can also apply the same exercise also for the perturbations, and we can use growth rate data. So in this case, okay, I'm going to jump through some of the technicalities. So there are also some growth rate compilations with some caveats, okay? Of course, you can find the compilations in these references. This is how the data, the F-sigmite data look like. And again, you can fit them and you can do the same exercise and get some expression with a genetic algorithm, and then ask yourself, how can I interpret that? And for example, what information can I get out of these things? And there are also some other kinds of data called the EG data. Again, I don't have so much time, but this data give you information on the anisotropic stress. And then if you do the same kind of exercise, there are some compilations, you can feed them, blah, blah, blah. You can do the same exercise. You can find some details in the papers. Then, for example, you can get some constraints on the anisotropic stress. Okay. Now, the way we have defined in this case anisotropic stress is the ratio of the two Newtonian potentials, and in general relativity, this has to be equal to 1. But we found in this case that there are actually strong deviations from unity. Okay. Of course, we are not claiming, even though they are quite strong, we are not claiming that we have discovered like new physics. We would like to have discovered new physics, but unfortunately, in this case, the data that we use, this EG data, okay, that come from lensing, they are notorious for having lots of systematics and so on. So in particular, this compilation, I think it's clear that it suffers from the systematics. So we cannot really claim that we have discovered new physics. Okay. Okay. Then the last 2 or 3 minutes, I would like to also say that we have applied the genetic algorithms also to doing forecasts for various collaborations, so in particular in Euclid. So there was a recent paper where we tested the duality relation. So what is the duality relation? So the duality relation is also, it's also known as a Farrington relation. So it's a relationship between the luminosity distance and the angular diameter distance in any metric theory of gravity where the number of photons is conserved. This expression is always true, okay? And if we find deviations from this consistency relationship, then this means either we don't have a metric theory of gravity anymore, so it's not GR, it could be something crazy, I don't know, or perhaps the number of photons, which is more plausible, is not conserved. So perhaps some of the photons, as they travel towards us, they get converted to axions and so on and so forth. Okay, So perhaps this is a very nice way to detect actions. And how can we do this? So the way to do this is we rewrite this expression in terms of this parameter eta, which is the ratio of dl over dA times 1 plus z squared. And usually people parameterize this as 1 plus z to some power epsilon, where epsilon is a small number. It could also be redshift dependent, but it's a small number. And if eta is not 1, then we can assume there is some deviation from unity. Okay. And of course, there are also some specific models that we could compare this against, like some action models or whatever. And we found, using this approach and using Euclid mocks, we found that Euclid will be able to constrain this eta parameter to a few percent, to 1 or 2% in small redshifts, and to like 4 or 5% at higher redshifts. Okay, so Euclid is going to be really amazing. This was a paper that appeared about a year ago. And we also did another application of this thing. So we wanted to put some constraints on varying alpha models. Now, if we have a scalar field which is non-minimally coupled to the electromagnetic field, then this will make it will force the fine structure constant to vary with redshifts, and this could have a very distinct imprint. And again, we found that Euclid will be able to constrain either deviations, this delta alpha over alpha directly, or if you assume some linear approximation, it will be able to constrain this coupling zeta to a few percent, both at intermediate and high redshifts. And actually, Euclid will be able to recover the fiducial model. So for example, what I call here zeta 0, W0, WA is the fiducial model. So it's this model that we assumed. And you can see that the genetic algorithms was able to recover the fiducial model quite well, actually. So the fiducial model is a dashed line, and the genetic algorithm is within 1 sigma in all cases. So it's not up there, it's not down there. I mean, it follows the fiducial model quite well. Okay. And the last thing that I would like to say is that we can use the genetic algorithms not only to discover new physics, but we could also use it to improve various fitting functions. And one particular example is the sound horizon of the drag redshift. So what is this thing? So the sound horizon of the drag redshift is the scale of the baryon acoustic oscillations, and it's given by the integral of the sound speed of the baryon photon plasma over the Hubble parameter, and this is integrated from the redshift of the drag redshift until infinity practically. And the problem with this integral is, even though it's a very innocent integral, apparently, I mean, someone might say, okay, I can do it numerically, but the problem is that it depends on the redshift at the drag epoch, and we can only calculate this by using recombination codes like recfast and high-rec. So this is a bit computationally expensive. So people, what they have done is they have created fitting formulas. So for example, the well-known one by Eisenstein and Hu, okay, which is actually accurate only to 2%. And this depends only on omega matter and omega baryon. Okay. And the problem with this is that we found in a paper with my student Ben that if you try to do some Monte Carlos with this, then you get results which are actually biased. So if you compare, so here I'm showing some contours of omega matter and RSD. And if you compare the contours you get by using the Eisenstein and Hu approximation, which is the blue line and the blue contour, then you can see that with respect to the full numerical one, by using the full Boltzmann code or the genetic algorithm fit, then you get a bias which is like 0.5 sigma. So practically you are biasing your contours for nothing. Okay, so this could be a problem. On the other hand, what you can do is you can make grids of parameters using high-rec, and you can create a much improved fitting function given by this expression, where these numbers actually came by the genetic algorithm. We didn't put it by hand. So what we did is we created grids of parameters, threw them at the genetic algorithm, and then the genetic algorithm after half an hour or 1 hour gave us this fitting function. Okay, and we found that it's actually accurate to 0.018%. So as I said, the Eisenstein expression is like 2%, and this is like 0.02%. So it's like 2 orders of magnitude improvement. Okay, and this is the last thing I wanted to say. So I would like to now summarize. So I gave a very brief introduction to a specific machine learning approach called the genetic algorithm, which is inspired by evolution. It's a stochastic optimization approach. As I mentioned, is very similar to a Monte Carlo, but instead of doing a random walk on the parameter space, you are doing a random walk on the functional space. So it's a bit more abstract, but it's very similar to the traditional Monte Carlo and Bayesian approach. Okay, you can practically do almost everything that you do with traditional approaches. And I presented very quickly, first of all, how the genetic algorithm works. This simulation that I showed you. I showed some applications to real background perturbation data, some null tests, forecasts from Euclid, and finally some fitting functions. And I think it's clear that the future is bright for machine learning. One last thing is that you can find this code in my GitHub. So for now, the code works with Mathematica, but I'm planning to port it because some work we are doing in Euclid. I'm planning to port it also to Python. And on my website, you can also find some other stuff you want to play with Monte Carlos and stuff like that for educational reasons. Okay, thank you.
Thank you.